Okay, so the topic of my lecture today is continuum breakdown and the need for molecular description of gas flows. Sorry, okay. So, brief outline of my lecture. So, I'll be talking about continuum versus molecular approach, then markers of breakdown, equilibrium breakdown or continuum breakdown as it is used in the literature. Then slip and temperature jump corrections, Burnett and higher order equations, just a tangential touch upon that. Then the molecular statistical approach that are typically followed. And then the molecular models and interaction potentials. It's just an introductory lecture, okay? So, as you know, a fluid can be described in two completely different ways, but still they are very contributing ways. Okay, so both methods are complementary. When it comes to the continuum approach, so the continuum hypothesis is that on a scale which is much larger than the molecular dimension, okay, fluid can be considered as a continuous medium. So, of course, you know that the reality is that fluid, essentially, gas is composed of molecules, particles. But you ignore that reality and you consider it to be a continuous medium. And then you have you have a model for governing the variation of certain properties that you ascribe to this medium. Okay, and these properties are pressure, temperature, velocities. And then you have a model that gives the spatio-temporal variation of these quantities. And these models are nothing but continuum models. One of those is Navier-Stokes equation based on the conservation of mass, momentum and energy as told by Professor Myon. Okay. On the other hand, the molecular approach wherein you consider that fluid or gas is essentially made up of molecules. These molecules randomly move, okay, and in doing so, they transfer the mass, momentum and energy from one place to the other. Okay. So therefore, these molecules, the behavior is now governed by the laws of dynamics or kinetic theory. When you consider these molecules, the number of molecules per meter cube or per unit volume is so large that you cannot practically deal with each and every molecule and its dynamics, which means collisions with other molecules. So what you do is you do the statistical description of gas flows, which means like how many molecules possess this much of velocity, okay? Which means then you start talking in terms of the distribution function, velocity distribution function, okay? So it is a fraction of molecules belonging to a particular velocity or a particular energy level. So therefore the governing equation is the Boltzmann equation or a simplified model kinetic equation. One of those is the BGK equation, okay? And then, but finally you have to come from the pixel to the picture, macroscopic picture. So you have to get that because you are interested in macroscopic properties, because you are measuring the macroscopic properties. So you want to get back the macroscopic properties from the microscopic data. Okay? So either you sample the particles or you consider from the statistical description as told by Professor Myon, you integrate those over the velocity space and you will get the macroscopic properties. And statistical mechanics provides the link between the microscopic description and the macroscopic description. Okay. Now, having understood the two different ways of looking at fluid flow, then there should be different methods of analyzing the fluid flows. Okay. So in fluid dynamics, we can have three different categories of methods. The first one is macroscopic method based on the conservation laws. And here we talk in terms of the Navier-Stokes equation, base CFD, wherein you need the constitutive relations or constitutive laws. We'll talk about those in in this course, pretty in a much deeper level. Then we consider and also the length scale associated with the macroscopic method is something of the order of 1 centimeter to 1 meter. Okay. Then we consider the microscopic method, the bottom one. Okay. This microscopic, it's a kind of a sort of a misnomer because not really here the length scale is in the microns. Actually length scale is in nano or angstroms. So mostly the method which is most popular here is the molecular dynamics method, where it is an atomistic method, and wherein you consider the motion of molecules, okay, in the physical space, and you just kind of integrate the equation of motion, the Newtonian equation of motion, and that's how you get the overall the description of the fluid flow when you integrate that picture. Now you can have classical molecular dynamics, which ignores the electronic structure. You consider a molecule as one, particle or a spherical particle. With, of course, it could have multiple atoms, but you ignore the electronic structure. Or you can go to much deeper level like Born, Oppenheimer, molecular dynamics, which indeed considers the electronic structure. So it all goes through the details of a molecule, how you model a molecule. Now, in between them, we have mesoscopic methods, wherein the length scale is of the order of, like, it could be from centimeters to micrometers and so on. And here we have three popular methods. The first one is the lattice-Boltzmann method, which is based on the VGK equation or the model kinetic equation, simplified Boltzmann equation. But yes, it is discretized in the velocity space and also in the physical space. The second popular method, which is widely used for hypersonic rarefied gas flows, is the direct simulation Monte Carlo method. I'll come to it in details in the next lecture probably. Okay, but yes, here we do not solve the Boltzmann equation per se. We do the direct simulation of gas flows, the way flow really develops. So we introduce molecules and let them move and collide with each other on the surface. That's how the flow develops, evolves. And then of course we can have the VGK equation solvents. Okay. Now, when it comes to like the continuum versus the microscopic or molecular description of fluid flows, so it's important to understand the continuum limit. When and how we should which model. So suppose you take the continuum model or Navier-Stokes equation, for example, you should be aware to what extent you are able to, you can afford to use this equation, because it's a model which has a finite range of applicability. So in fact, Professor Myung was also telling, so when it comes to continuum models, we deal with the fluid particles. Okay, these fluid particles are in reality, of course, they are composed of molecules, but in continuum model you do not consider this. Okay, but here, if you consider a fluid particle, then fluid particle must be composed of large number of molecules, so that the statistical averaging would work. Okay, if you compare this picture with this one, this box, okay, the red box, which consists of a few molecules, okay, of course it's a representative picture. You consider that a fluid you have a very small fluid particle, so that the number of molecules in this fluid particle is very small. So would you be able to do the statistical averaging? Would you be able to do? No, right? Because it would fail beyond certain extent, because you will not be able to capture the signal, the statistical fluctuations will be so large. Okay. So as long as the statistical averaging works, you can afford to use the continuum model. It could be with corrections, like as mentioned by Professor Myung, with slip and jump conditions, corrections to the boundary conditions, or something else, maybe higher order corrections to the constitutive laws. But as long as the statistical averaging works. If it doesn't work, then you have to consider the molecular description of fluid flows. Okay, and then go from the pixel to picture approach. Okay. So now under what conditions statistical averaging could fail? Primarily you can think, suppose you have a very small length scale, for example, your characteristic length scale is very small. You are dealing with the microfluidics or nanofluidics, wherein you have micro or nano channels. So at the nano length scale, you'll have very few molecules. So your statistical averaging may not be really right. Okay. The another condition is, as you go higher up in the altitude, beyond certain altitude, the number of molecules per unit volume is so low that again the statistical averaging would start failing. So there could be straight away two scenarios in which we have to think of looking beyond the continuum description of fluid flows or making corrections to the continuum model. Okay. So another view, if you consider the Navier-Stokes equation for incompressible flows, this is very familiar to you. Of course, I have written in the differential form. Okay, so it is applicable to a point. Essentially, it's this expression is nothing but F equals ma. Okay, ma, and this is the forces on the right hand side, the pressure force and the viscous force on the right hand side. This gives the acceleration. Now, if you consider the viscous term, okay, it looks like this. This is called its constitutive law or equation. Now, for Newtonian fluid, you get this relationship between the shear stress and the strain rate is linear, and the coefficient that we have here is nothing but the dynamic viscosity. Now, viscosity is an interesting property. It's a transport property, okay, which, of course, for a fluid, you know that fluid is something that deforms under any amount of shear stress, okay. But yes, it of course presents resistance to being deformed. Now, this viscosity is a property that represents that magnitude of fluid's resistance to the deformation rate. But essentially, it's a transport property associated with the momentum transfer. And one consequence of this property is the no-slip condition that we have been using in CFD quite a bit. Okay, which means that no relative motion between a fluid and solid boundary. Whether it is really true under all conditions? No, it's not. So, if you look at the dynamic viscosity more closely from the microscopic perspective, okay, and if you use the basic laws of statistical mechanics, okay, you consider the molecular picture, you have the molecules in the fluid domain, and you consider the random motion of molecules from one region to the other, okay. So you will find that due to this random motion of molecules, a momentum gets transferred, okay, in the direction of the flow from the higher velocity region to the lower velocity region. And that's how you get the relationship, the same relationship between the shear stress and the strain rate from the basic statistical mechanics. And here, if you apply this, what you will find is that your mu, the dynamic viscosity, is defined like this: 1/3 rho. This c dash bar is nothing but the mean thermal speed. So c dash bar would be nothing but 8 RT over pi, where R is the specific gas constant. Now, if we look at it in more details, you will find that this expression is only true when mean free path is very small. If mean free path, which is the average distance between two successive collisions of a molecule, if it is large, then this expression is no longer valid, and you will come up with, or it will give you the higher order terms. The relationship between this, the shear stress, and the strain rate will get complicated in the sense that you will have higher order terms. So therefore, at large mean free path, or as you go to high altitudes, these higher order terms should appear in the continuum equation. Okay, and therefore you need to consider modifying the constitutive relationship, the linear relationship. The same is also true for viscoelastic fluids. Okay. Now, when is continuum hypothesis valid? Okay, so the first few, the idea behind the Knudsen number. This is, of course, what I am going to say is going to be consistent with what Professor Myung said. But initially, the Knudsen number was proposed as an indicator of non-equilibrium. Okay. What is this Knudsen number? This is nothing but the ratio of the molecular dimension, which is the mean free path most of the times, to a characteristic length d. Okay. We shall have a discussion on what should be this characteristic length scale, because it is also not very straightforward. It depends on the individual problem. Now, based on this, if you want to describe, okay, the validity of continuum hypothesis, then you will find that you could have, okay, here if you see, here we have the Knudsen number on the X scale, and validity of different models on the are shown here. So if you see, the Navier-Stokes equation are typically valid till a Knudsen number of 0.1 or so, and with the addition of velocity, slip and temperature jump corrections to the boundary conditions, the model can be or has been seen to work till a Knudsen number of approximately 1 or so. Whereas if you see the Boltzmann equation, it has a wide range of applicability. Okay. In fact, as you will see later, the Navier-Stokes equations can be obtained, or any macroscopic equations of the conservation laws can be obtained from the Boltzmann equation, actually by the method of moments. So based on this, we could have three scenarios. One is that we can have rarefied flows, in which you need to consider the Boltzmann equation, or you have to look beyond the Navier-Stokes equation model. In the rarefied flows, the mean free path is of the order of d, the characteristic length scale. Okay, so which means the Knudsen number is large here. Okay, the second scenario is the micro nanoscale gas flows, where your d, the characteristic length, the global length scale, it could be of the order of mean free path. Again, this would make the Knudsen number large. And then the strong shocks, hypersonic flow or a sphere, for example, wherein the length scale is that of the shock thickness. If you want to resolve the shock structure, then this length scale is nothing but the shock thickness, and which is of the order of mean free path. Again, you need to consider the molecular description of fluid flows. So this is a simple description of the regime of flows in terms of Knudsen number only. Okay. Of course, when you consider the Mach number, the same effects will be pronounced. Okay. Now, based on this, of course, you describe the different flow regimes. Sorry, something is wrong here. And you have, as long as the Knudsen number is less than 0.01 or so, you consider it to be continuum. 0.01 to 1, even a little beyond that, it's slip flows. Okay. Traditionally, then transitional flows is 0.1 to 10, and beyond 10, only in terms of Knudsen number, it's free molecular flows. Okay. Now, when it comes to the slip flows, then the Navier-Stokes equation, because the Knudsen number is still very high, the Navier-Stokes equation can still be used, but with corrections to your boundary conditions. So what are these corrections? So you will find that when Knudsen number is, or it gets larger, you will find that on the surface you do not have this no slip condition valid, and you have to implement the slip condition, okay, such that there is some finite relative motion between the gas and the surface. Okay. And these corrections were first given by Maxwell. So we could have the correction for the velocity on the surface. This is the simple expression that we have for the velocity slip. Us represents the velocity slip on the surface. Uy0 is the gas velocity on the surface, and Uw is the wall velocity. So U gas minus Uw at the close to the wall is given by this expression. Now where this sigma is an interesting parameter. It represents the tangential momentum accommodation coefficient. Please do not worry about these terms, they will become clear to you. But here, this sigma, what it describes is, suppose you have the gas which interacts with the surface. So how well this gas is getting accommodated with the surface conditions. This is what is described by the sigma. And it straight away depends on the time that gas molecule would spend with the surface. If a gas molecule is able to spend more time with the surface, it would have got accommodated with the surface conditions. If it has less time, it would not accommodate with the surface. So accordingly, you can have either the diffuse reflection, like you would have done in the radiation part, the diffuse reflection, or the mirror-like reflection, depending on the residence time of this gas molecule with the surface. So this sigma accordingly defines the same. Okay. Lambda is the mean free path, and du over dy at y0 is the velocity gradient on the surface. Now, so at ordinary conditions, your lambda is very small, the mean free path is very small, less than micrometers. So your slip, velocity slip will be very small. You can afford to neglect it. But as you go to higher altitudes, your mean free path would be larger. Therefore, this term could be important. And the same has to be implemented in the boundary conditions, that you have this much amount of slip. Using this simplified model, this is the first order model, you can have second order models and so on. Of course, Professor Myong has worked on that as well, and there is something called Langmuir slip model, if I am not wrong, which considers the absorption of the gases on the surface. But at the same time, if you consider the micro and nanoscale flows, there even at the terrestrial conditions wherein you have very low lambda, but you can have very high velocity gradient because of the small length scale. Okay. So again, this term could be effective even at the micro and nanoscales, because by virtue of the last term, du over dy, the velocity gradient on the surface. Okay. Similarly, we could have temperature jump on the surface. Again, the temperature of the gases may not be same as the temperature of the surface under rarefied conditions. Okay. Again, a similar expression where alpha is the energy accumulation coefficient. How well the gas is getting accommodated with the surface in terms of energy. Okay. Now, when you go to little higher Knudsen number, okay, and then Professor Myong was showing Chapman-Enskog expansion. I mean, wherein you make corrections to the. Suppose you say that your system is in equilibrium and then you perturb it out of equilibrium. Then you have to consider some added terms to the distribution functions that define the equilibrium state. So depending on the number of terms that you add, okay, you can have different continuum models. For example, if you consider second order corrections, you will have the Navier-Stokes. Then the third order will give you this, the Bernard equation. Okay, so you could have higher order viscous and influx terms. Here I am showing the viscous term for the Bernard equation. Interestingly, if you compare the first term, the leading term of the Bernard equation, to the viscous term in the Navier-Stokes equation, if you consider the ratio, you will find that the ratio is nothing but this Mach number times Knudsen number, which is consistent with what Professor Myong has been saying. That it's not only that the Knudsen number matters, but it's the product of Mach number and the Knudsen number which needs to be considered. Okay, together. So you can have a situation, as he was saying, that you can have a situation that your Mach, Mach number could be very large, but it's the product that matters, or other way around, even your Knudsen number could be large, okay, but the Mach number could be very low. So accordingly, you have to consider an appropriate model, which is based on the product of the Mach number and the Knudsen number. The same is described by this, okay. But in this case, when you have the Bernard equation, you see that you get some higher order terms for the viscous stress, the shear stress, okay, and you will also see the terms for the temperature gradients, which are known as the Bernard thermal stress. Now, under what conditions we need to consider this, the Bernard equation? So there could be two conditions. First is where your Mach number and the Knudsen number is large. Okay. Then you need to consider the Bernard model, Bernard continuum model. And of course, when you do that, you will have to implement more boundary conditions. But this model also suffers, or has been reported to suffer from stability related issues. The other condition in which the Bernard equation needs to be considered is when you have low speed but highly non-isothermal flows. Suppose you have large temperature gradients along the surface. In that case, these terms could be large. So then you need to consider the Bernard thermal stress. Okay. Now, if you go to further high in terms of the degree of non-equilibrium, which is given in terms of Mach number times Knudsen number, the product of those, then we need to consider the molecular description of gas flows. So let us now consider the molecular description of gas flows. Let us start with the definition of a gas, okay, and how it is different from the solid and liquid. So, of course, the three states of matter can be distinguished because of the intermolecular forces, or in terms of the mean molecular space that exists between the molecules. So, intermolecular forces and of course the shape and the volume. Now, when you consider a gas, so typically an ideal gas, as you know from your high school physics, that an ideal gas is something for which the intermolecular forces can be neglected, or molecules do not interact until and unless they collide with each other. So, that is how you define an ideal gas. Now, under what conditions it is true, and how do we consider the departure of a gas from the ideal state, and what are the effects of temperature on the model that we considered in describing a molecule or a gas. So then, what is a molecule? The molecule is something that characterizes the substance or the gas itself. Okay, it is the most basic entity, elementary entity that describes the properties of a gas. Now you can have three kinds of gases. You can have monoatomic gases, you can have diatomic gases, and you can have polyatomic gases. Now a monoatomic species has only the translational motion. It can only move in the space, in the physical space. Okay, it can move in three independent directions, x, y, z. When it comes to diatomic species, it can not only move, but these can also rotate about the axis. So accordingly, you will have the rotational mode becoming active when you consider the diatomic gases. At the same time, if you consider this basic spring model, okay, this molecule can also vibrate. So you will accordingly have the active vibrational mode. Same is true for polyatomic species. You can have two different kinds of polyatomic species, the linear and the non-linear. Linear, for example, CO2 is a linear polyatomic molecule. Polyatomic means it should have three or more atoms. When it is linear, again, it depends how many degrees of freedom would be active for each mode. For example, translational, there could be 3 degrees of freedom active. When it comes to rotational, for the diatomic and the linear polyatomic, you will find that there will be only 2 rotational degrees of freedom effectively. Okay? It's because the moment of inertia about this axis would be very small. Okay? Now, you will have the moment of inertia about this axis and the z axis, but the moment of inertia about this axis is very small. So ignore that degree of freedom. So effectively you have 2 rotational degrees of freedom. You have 2 here, whereas you have 3 rotational degrees of freedom. When it comes to the vibrational degrees of freedom, it becomes little complicated because it becomes temperature dependent. Okay? So depending on the temperature, you can have different active vibrational degrees of freedom. At low temperature, the active vibrational degrees of freedom could be as low as 0. Whereas at a temperature close to the dissociation temperature of the gas, you will have the most excited state of the vibrational mode. So it depends on the individual gas. And therefore, when we consider the molecular description of a gas, or when we develop a molecular model, these things need to be considered. How do you describe a gas? How do you consider the basic, how do you describe the molecule? Because it all depends on the details. Here in this picture, we are completely again ignoring the electronic structure. So for example, if you consider the TSMC method, okay, then even for describing this diatomic gas, we do not describe it this way. We consider it as a single particle. But the degrees of freedom would be accordingly assigned. Suppose for a O2 molecule, you will say that at normal temperatures, room temperatures, it will have 5 degrees of freedom. 3 for translational, 2 for rotational. You will not describe it in this manner. Your molecular model, it will be just a particle, a spherical particle, a point-sized particle actually. When it comes to MD, the molecular dynamics, then you can describe a a molecule really like this, the two atoms connected by a bond. That is how you would describe an oxygen molecule using classical molecular dynamics. Again, when you consider Born-Oppenheimer molecular dynamics, then you will also consider the electronic structure of this molecule. Okay, so that's about the molecular model. Now, how you choose a molecular model is that you should be able to get back the macroscopic, the bulk properties which are measurable. For example, from the previous, molecular model, whether you are able to get back the specific heat capacities at constant pressure or constant volume. I mean, the first kind of verification of the molecular model, and even more the bulk properties such as dynamic viscosity. Let us consider the ideal gas equation of state, which is given in different forms like this. Let us be aware of the different terms that will be used in this course. Here, of course, rho RT at P equals rho RT is the most known form, where rho is the density, mass density, R is the specific gas constant, T is the temperature. It could be written in this form, N kVt. Please understand this N is number density, number of molecules per unit volume. You can also write, and kV is the Boltzmann constant, by the way. Okay? You can also write the same equation in this form, where N sub M, this is the number of moles, and R0 is the universal gas constant. If you bring the number of moles in the denominator on the left hand side, the form that you get is PVN equals R0T. And why we are interested in this form, it will be very clear soon. Where Vm is the molar volume of the gas per unit mole. Okay. Now, when it comes to ideal gas, we consider that the intermolecular forces are negligible. At the same time, we say that the volume of molecules per mole is negligible as compared to molar volume. Okay, this is important. The volume of molecules per mole is negligible compared to the molar volume. Okay, so one volume is the macroscopic volume, and this is the total integrated microscopic volume comprising of molecules. But how about the validity again of this equation? Okay, so whenever we use equation, you should be concerned about the validity of the same. So the validity is this ideal gas equation of state in this form is valid at low pressures and high temperatures. Why so? You can think of it a little bit and then come back to me. But let us remember that this is valid at low pressure and high temperature. So that is the idea behind, if you consider the real gas effects, real gas means when you have the opposite conditions of high pressure and low temperature. For example, cryogenic temperatures, you will need to consider a different equation of state or modification to this equation of state. Or when you have high pressure, then the number of molecules per unit volume is so large that intermolecular forces cannot be considered to be negligible. Again, you need to consider a correction to it. So the two corrections that we will consider in this lecture are van der Waals equation of state, P plus A over Vm square Vm minus B equals R0T. That's why we use that PVm equals R0T form of the ideal gas equation of state. Here you have A over Vm square correction for the intermolecular forces that are significant when you have high pressure. P is the correction for the finite volume of the molecules as compared to that of the gas. Now, interestingly, these parameters A and B can be obtained from the critical properties of a specific gas. And you can write this equation in terms of the reduced quantities, reduced or normalized by these critical properties. And you will have the universal equation of state, universal van der Waals equation of state, which you can apply. The other equation is Viral equation, which is given by this, okay, wherein you consider, you write PVm equals R0T. The left hand side is also known as the compressibility factor, which is written in terms of this kind of expansion. Okay, this is expansion in terms of the molar volume. A1 and A2 are the coefficients which are known as the virial coefficients. Vm is the molar volume. Okay. Now, interestingly, at low pressure, we can ignore the third term on the right hand side and so on. We need to consider only the two terms at low pressures. And you will find that this A1, the virial coefficient A1, describes nothing but the Vm minus Vm ideal. Now what is this? This is the molar volume of a gas at real condition as compared to that of an ideal gas. So this is an indicator of the departure from the ideal gas state. Okay. Interestingly, the same coefficient A1 can be given in terms of the interaction potential between the molecules or intermolecular force. And this expression is given like this. Please understand that this Na is Avogadro constant. UR is the interaction potential between two atoms separated by a distance r. Now this separation is between the centers of the two atoms. And this UR here we are this is capital R. This U interaction potential is in here is considered only a function of the distance between the two molecules, the centers between the two molecules. So now in this model we have this connection between the equational state, the parameter that comes in the equational state, and its relationship to the interaction potential, how molecules do interact. So that is the first time where you see the effect of the interaction between the molecules onto an equational state. Equational state is, it describes the thermodynamic state of a system. Okay. So therefore, let us now consider this interaction potential. Okay. How molecules do interact with each other. Of course, you can have many more equations of state, but here we are considering only two. So now, so having understood that, so we started with the assumption now that beyond at some point of time, okay, when some conditions we feel that they are violated, we need to consider the molecular description of gas flows. Now, in the molecular description, you need to have the molecules, which means you need to construct the molecular model. How good or bad you can design, because you have the limited computational capabilities. So accordingly, you have to know the computational capabilities that you have, and then accordingly you have to consider an appropriate molecular model. After choosing the molecular model, you need to consider how are these molecules are going to interact with each other. Okay. So this is very important in the molecular description of fluids or gas flows. Herein, let us consider one popular interaction potential. It's a model potential. Why model? Because the way the two molecules are going to interact with each other, okay, is truly very complicated. It could be highly complicated. And how can you describe the true interaction between the two molecules? This is again a very complicated subject. Okay, so you may have to go to the theories which are subatomics. For example, DFT, density functional theories, or you may have to do the molecular beam scattering experiments to get to really know how two molecules are going to interact with each other. So therefore, but we would still like to describe the interaction in the most simplest way, okay, which still represents the essential physics of the interaction between the molecules. And that is why we refer to this as the model potential, not the true potential, not the exact potential. So in this, let us consider the Lennard-Jones potential. In this Lennard-Jones potential, on the y-axis you have the U, the interaction energy, interaction potential energy, and as a function of R. Okay. Now this R is the distance between the centers of the two molecules, and This is shown here. The relationship, it's from John Leonard Jones. This relationship for the interaction potential energy in terms of R is given by this simple expression. In here, you have two kinds of interactions. If you see this cartoon, this picture, you will find that beyond this line, you have the repulsive forces coming into the picture between the two molecules. And beyond this line, you have the attraction. So what are these forces? As you know that when two molecules approach each other, okay, they could perturb each other's electronic structure. So you can, what happens is that there is a formation of temporary dipoles, and you have the temporary dipole moment acting between the two molecules, which makes them kind of interact with each other, and then the nature of interaction is such that it's attraction in nature when the distance between the two molecules is reasonably large. When the two molecules get too close, then the electron cloud then starts overlapping, and because of that you can have the net repulsion between the molecules. Now here, this distance, okay, or this location is very important, where you are getting the interaction potential 0 at this location. And of course I have forgotten to show here, so if I will show this here, this is your U and this is your R. So the behavior is something like this. Here, this location, this distance is nothing but this sigma. Okay. Now the importance, this sigma is a very important parameter because this represents the length scale, okay, at which molecule the interaction between the molecules is very significant. They start repelling each other very significantly, okay, because as you see, this goes repulsive. I mean, there is a very strong force in repulsion. So molecules are strongly repelled at this length scale. So this is a very important length scale. In fact, you can use it to describe the diameter of a molecule, because there is a length scale at which the molecules really start repelling each other and the two molecules would simply go away. So it can be used to describe the diameter of a molecule, because otherwise if you think, it's easy to say that the diameter of a molecule is 3 angstrom, but if you really think about this, it's very difficult to really define the diameter of a molecule. Okay, so this is one such measure which defines that. Now, yeah. What was that?
The significance of positive and negative value.
Yeah, see, you have this attraction force, right? And then the repulsion starts. But this is the net effect of that. Okay? So you have the attraction and the repulsion. Beyond this, it's the repulsive part which becomes prominent, because you have the, this relationship. The second term on the right hand side, it gives the attraction, and the first term on the right hand side, it gives the repulsion. Okay, so accordingly the combination would give you a value. I forgot to mention this. Here the sigma over r to the power 6, this is the attraction term, and sigma over r to the power 12 is the repulsion term. Interestingly, why it is sigma over r to the power 12 is, it has been chosen such that it kind of approximates this behavior really well. At the same time, you can save the computational time, because the sigma or r to the power 12 is nothing but square of the right hand side term, sigma or r to the power 6. So therefore, when it comes to the molecular description of gas flows, the model that you choose, it is not just based on how well it can capture the physics, but also it is based on the limited computational resources that you have. Okay, so sometimes you have to make a trade-off between the accuracy and the numerical efficiency. Sometimes you would like to go for a very sophisticated, very advanced model, but you do not have resources to really do the computations. Because please remember that when you describe the fluid flows at the molecular level, okay, then you have to do millions and billions of calculations, okay, every time step, which involves many billions of the floating point operations. Okay, so essentially it's all about the efficiency and the accuracy. Now this depth here, this is known as the energy well depth. This and this is given by the symbol epsilon. Okay, and that's how you have this epsilon coming in here. It represents the energy well depth. Okay. Again, how well you are able to represent the interaction between the two molecules is given by these parameters sigma and epsilon in this particular model, the Leonard-Jones model. And depending on the epsilon value and the sigma value, you should be able to see the qualitative behavior of different gases, whether you are able to reproduce the behavior of gas at the qualitative level and then at the quantitative level. Okay. For example, if you consider different gases like oxygen, nitrogen, and for example helium, whether this model can really give you the correct boiling point, for example, just an example, okay, it would depend on the values that you choose for sigma and epsilon in this model, the Leonard-Jones model. Okay, please understand that here it is mentioned beyond r equals 2 sigma or 2.5 sigma many times it is taken. Beyond that distance, we consider that the forces between the two molecules which are neutral have become weak. Okay. Again, it would depend on the kind of molecules that you are dealing with. If they are neutral, then the forces between them that are acting, they are because of the temporary dipoles, and these dipoles are transient in nature. As molecules have passed by and they are now distant, then these temporary dipoles would go. But again, if you have a polar molecule, okay, which is interacting with a neutral gas molecule, or a polar molecule interacting with another polar molecule, then you will have different kind of potential that would exist between the two molecules. Okay, so again, it would depend on the molecule to molecule how you choose this potential. Let me describe two simple potentials that we typically use in direct simulation Monte Carlo method. The first one, which is the simplest potential, Hart-sphere potential. Here, Hart-sphere means it's also known as billiard ball potential, because in this model, it's again a model potential in which the attraction forces are completely ignored. You say that the two molecules approach each other and they interact only when they physically touch each other. And when they do so, they will completely repel each other. Okay, they cannot cause any kind of deformation because the forces that exist between the two molecules are so large that immediately they will be, they will bounce off each other. So that's the idea behind the Hart-sphere potential. So it's an impenetrable wall at the junction of the two molecules. Okay. So it's not a soft sphere potential, please understand. That is why it is called a hard sphere potential. When you consider soft sphere potential, which you need to consider, for example, if you are dealing with grains or sand and so on. When you consider a soft sphere, then you also need to consider the deformation of the molecules. Here it is hard sphere or billiard ball. Now, why do you choose this potential as simple as this, in which molecules do not interact until they really collide, at which they simply bounce off each other? It's again guided primarily by the computational sources. You want to save on the resources, but still from numerical experiments, you have to do the numerical experiment, and as Professor Young said, you need to do the verification of the model and then the validation of the model with respect to the experimental data, whether it is able to reproduce the qualitative behavior at the lens and then the quantitative. Of course, hard-sphere potential is a very simplified potential, the most simplified potential. Typically, the potential that we use in direct simulation Monte Carlo, DSMC, is variable hard-sphere potential. variable hard-sphere potential is an improvised hard-sphere potential. Again, we do not consider any attraction forces. But the change here is that the sigma, which is again a measure of the kind of the range of interaction between the two molecules. To what range a molecule can have an influence on the other molecule. Okay, so it determines the range of or strength and the range of the intermolecular force. Now, in the variable hard-sphere potential, the sigma is a function of relative velocity between colliding molecules. Please understand this from this, the behavior, the intuitive behavior that you can kind of imagine, that if a molecule is really, kind of moving slowly, and you have the stationary molecule, let us consider the motion of a molecule relative to a given molecule. So let us consider one molecule stationary and consider the behavior of the other. If this molecule, which is approaching the stationary molecule, is moving very slow, you would see that the influence of the stationary molecule would be felt to a larger distance. Why so? Because again, the time for which they are interacting with each other would be large. When this approaching molecule is moving very fast, the time of interaction is very low. So accordingly, this sigma, which is the range of interaction, should be intuitively a function of the relative velocity between the two molecules. And that is the primary idea behind the variable hard-sphere potential. That is one of the most frequently used potential in the DSMC method. Okay. Of course, you have more sophisticated potential. For example, you can have the soft sphere potential, wherein you consider the attraction forces, and you can even go on kind of making or using a more advanced or more and more accurate model. Okay, wherein you really need to, how do you get this? How do you really see whether a model is really working? Again, these are numerical experiments. So if you are, suppose you have a few models available to you, then you choose, you do the experiments, and then you see or develop a feel for the individual model, and then accordingly for your application you may have to choose. So for example, in molecular dynamics, typically we go for the Lennard-Jones potential for the interaction between the neutral molecules, and of course for the polar molecules you have much advanced potentials. For example, tip 4p or tip 3p, tip 3p, right? I tend to forget the 4p, also potential for the interaction between the water molecules. Okay, so I think let me end my lecture with this. In the next lecture, we will go beyond the interaction between the molecules, and then we shall consider the Boltzmann equation, and then we will get to the DSMC method. Okay. Thank you so much.